Alrighty, good morning. Welcome to IO 310, Sandboxing Your Containers with gVisor. I know that the keynote is still going on, so thank you for coming from the beginning, so I'm very excited about that. My name is Yoshi. I'm product manager on Google's Kubernetes Engine. I mostly focus on the multi-tenancy, which will include the Sandbox and gVisor that we're going to talk today, and Hardware Accelerator, which I gave a talk on Tuesday about GPU and the one that we launched, Cloud TPU, in Kubernetes Engine. So a little bit different, but that's what I do at work, and we have Ian here.
Yeah, and I'm Ian Lewis. I'm a developer advocate at Google. I focus on Kubernetes and on extensibility and security in Kubernetes.
Thank you. All right, then let's get started. Well, I think it's getting very, very obvious, but containers are really, really exploding. And if I look back, the kind of I'm a computer geek, and I've been looking into virtual machine, all the computer technologies for quite a bit of time. It's so kind of so impressive to see where containers and Kubernetes are today. Google has been investing in technology, containers for more than a decade, really more than 10 years ago. And it has been core part of how we run the service. And nowadays, we run like more than 4 billion containers kind of launching every week. And that's a really, really huge number. But when I look at back the kind of history, when Google started the container effort in the Linux community, it was more like a technology. And it was indeed used there. But I think we all agree that Docker container that came in around 2013 provide a huge value in terms of developer experience. So before, the container was one way of doing the computer isolation, but it became more like tools, right? Like tools and package and how you share it. And that was actually very impressive. At that point, I was not working at Google, but it was a very, very phenomenal thing to happen. Then Kubernetes come into play because Google had the experience of running the container in a large scale, and now people start seeing container rather than the technology more like a tool and to increase the productivity and portability. Then this problem about how do we deploy the container, how we run container scale become a much more important critical problem, and that's exactly why we open source Kubernetes today. So like this quote that it's beautiful, like Kubernetes, the Linux of the cloud. It's super impressive and super kind of amazing to kind of see that now how Kubernetes and the containers are helping people's day-to-day workflow that we're seeing today. Well then, however, as many kind of popular technologies, security becomes concerns, right? Like if your technology or product is not popular, not many people using, then, well, you can actually, a little bit lower bar the security. Well, I will definitely still advocate that security should be coming first. But in reality, if you're busy with something, it comes afterwards. But apparently, because containers on Kubernetes are so pervasive and widespread, now the security has become a real problem. And in fact, security, people who participated to the cloud native computing foundation. Folks did in the survey, security remains as the top challenge above anything. Like literally 43% of the respondents raised that security is the top one. And the others like storage and monitoring, networking. If you look at monitoring today, it's one of the hot sessions in this Google Next. But still, I think the security is the top one, and then you have a lot of sessions also that has been happening at this Next too. So I will strongly recommend that in addition to this talk, if you're interested in Kubernetes, I think a lot of talks have been, are going to happen today. But for those that happened, yesterday and the day before, strongly recommend to watch the video to augment the things that we're going to talk about. So, because I mentioned that Google runs containers for a long time, and that's true. So I get a lot of kind of questions like, okay, so how are you guys handling this isolation concerns around containers? And that's a very good question. And I feel lucky to be part of Google because I can actually ask the same question to my colleagues who are in this in this room. Like, so how are you guys running? How are you guys dealt with this? And not only the product or project, but I can also listen to, a lot of, back behind the scenes stories there. And hopefully this could be kind of interesting for you. So there's a very, very long history, like I said, like more than 10 years ago. So long history of really, iterating, trying and failing, but exploring the best way to run application with the proper isolation. So let's try, let's rewind the clock a little bit and see what we're, what we have done in the past. So take one, run as root. This is a very bold statement. I still feel kind of nervous to say so. I checked with my tech leads a couple of times. Is this real? Like, did you really guys run things at root? And the answer was yes. And apparently, nothing shields the system. Your process can basically access all devices there. Of course, you can access whole file system, the host file system, all resources available for you. You can configure network as you like, and you can perform any system calls, of course, and even you can send sigkill, sigkill to others. So it's pretty. And when I heard about this, I was kind of pretty impressed in a different way. And of course, what if it goes wrong? Of course, right? And this RM, RF, and star, still this kind of a sequence of characters make me nervous, right? I'm pretty sure that everyone in this room has kind of experienced this once or twice in the whole career and kind of regretted. Your data is gone, of course. But more seriously, that misoperation is, is a real thing, but more from a security context, what if the malicious software, take advantage of this? And basically, there's no answer. Right. So take two. Run as unprivileged user. Great. Yeah, this is we should do by default. So basically, give away the privilege of root. You don't need it. You have only limited access to those devices, including network devices. File system, of course, will be limited. And what kind of system calls that you can call will be also checked and block if not. And also the sending a signal capability will be also limited. So great, already good enough. But what if the process can have a capability to set the PID or like you can create a raw socket? You can still do something there. So now take three, dropping capabilities. Linux has a concept called functionality called capabilities, which would split the capabilities of that as aggregated to rule into a much more finer grain. Basically fewer capabilities, then basically you have you have a better isolation there. So for example, like loading a kernel module, which is apparently a big thing, admin capability, capability to setting the system clock, and networking, and the list goes on and on and on. So, okay, now we have the capability, so we somehow managed to set what a process can do and what a process cannot do. But what if a process can consume all the resources? What about the resource isolation? We don't have anything. So take four, C groups. So to address the resource isolation problem, Google has been, in the past, contributed this control group, which will allow limiting the resources and accounting them for better isolation. For example, it will limit access to the CPUs, and it will also account the CPUs by that particular C group. And same for limit and account for the memory usage. You could even assign cores and memories to memory nodes to a particular group. And also you can also control the access to the device based on which C group that you're in. Great. Now we figure out how what the process can do. Resource will be limited, but still a process can see others. It can still see what others are doing. Take 5, namespace. I actually didn't know, but namespace actually existed a long time ago. And I was looking, yesterday I was looking into it, in the past, this when the secret was proposed, this integration with Namespace happened at that time. So Namespace basically provides you that visibility, that isolation for each namespace type. For example, like a networking, PID, mount point, user, IPC, a lot of things. So with this namespace and also the resource limitation, resource isolation with C groups, it's a huge advance. Like, it's a huge improvement. I think it took quite a bit. Like, I'm pretty sure it was like 2 or 3 years when I started seeing a proposal from Google back in 2007-ish, I think. So it's a huge, huge improvement compared to what Linux was at that time. I think I'm not sure how it's doing today, but from the original concept was more from the Solaris zones. But I was always told that Linux doesn't have that capability. But at this point, I think it was very clear that now there's a so-called container capability inside Linux. So it's great. And I hope I'm done with talking about this. But life is unfair. Someone said a very inconvenient truth. Containers do not contain. It's a very short word, but it's so true. It points out the fundamental part that we will kind of talk about. This statement is really so powerful that it reveals what's a fundamental challenge about isolating processes in containers. But you might ask, I think I also wasn't paying so much attention until I realized this point, but you have some sort of isolation from a visibility, capability, and resource consumption. Why are we so focused on about this containers not containing? And I think it's a good question. So we're focused about containers not to contain because what we're discussing here is about the threats from the inside of those containers. And that will, like this picture, we're assuming this cute cat is the attacker and the victim or the parents there. You want to wonder, like, who actually put that cat inside the cage? Like, who actually put a thread inside a container? And yes, that's understanding that threat model is very, very important. There are two major cases. I mean, I think there are more detailed cases, but just very roughly two types. One is for if you're running a service that allows user to submit code, like SaaS and multi-tenancy. Like for us, perhaps Google App Engine could be a kind of a good example. Very obvious case, I think, that I'm aware of. If you're running a WordPress and you will perhaps allow users to use their favorite plugin or their own customized plugin, and there you go. You have a code that you haven't been able to certify, and that's one particular problem, a particular case that it could actually put the threat inside your system. The other one, which is somewhat relevant, is a security breach. So yes, attack, first of all, like firewall and everything. You would want to first prevent any threat coming into your system. However, we all know that we do our best, but there's something happening. So once that incident happens, the biggest principle that we have in Google in terms of security is that we have to have multiple layers of security. So if you only have one bar, then if that's compromised and then it gets in, then your entire system is at risk. But if you have an attacker coming into one of your container, if you don't have anything protecting or containing inside at that point, then all of a sudden one attack will be could affect the rest. So those are things that we wanted to be careful. And especially the latter case, if you're running a system for a larger organization, right? If you have a full control over what kind of code you go, I think your chances of getting to that problem is lower. But if you have a much more distributed teams with a lot of different kind of a background, then you may or may not be able to control that fully. So if you want to be, if you actually want more scale or like agility, then you actually might want to think about really containers to contain the threat inside. So when we talk about the kind of threat from the inside, what we're talking about is we're talking about attack through the Linux kernel, which will allow these containers to escape outside of the isolation that we talked earlier. They usually exploit bugs inside a Linux kernel through a system service, like obvious one, system calls, but like /proc files, and to bypass all the long history of the add-in mechanism inside Linux kernel, and bypass that, and eventually elevate the privilege. So escape, and then attack the kernel, and then break it, and take the privilege of the system. So this is the kind of a very high level. It's more detailed, but that is the kind of overall picture of the threat that we're talking, the attack that we're talking about. So Linux kernel, you may not notice because it's so widely used, and indeed it's great. It's a lot of people paying attention to security, but reality is that it has huge attack surface. Just by numbers, there are around 320, more than 300 system calls there. There are more than 2,000 CVs reported since 1999, out of which more than 200 are privilege escalations. So I'm not trying to actually really, criticize about the Linux kernel. It's like I said in the like I mentioned earlier, if your product code gets popular, then two things happen, right? You add more features that you have to respond to, more of those in functionality. Then the system gets complex. And then if you get more popularity, then you have chances of attackers paying attention to attack those, attack the product or project. Because, more audience, then they want it to be more effective when they think about the attack. One of the most famous one, I think, of that pattern of the attack is Dirty Cow that happened reported in 2016. It's a privilege escalation of vulnerability inside a Linux kernel. An unprivileged local user could exploit a race condition in the copy and write, so therefore cow, mechanism in the Linux kernel subsystem to increase their privilege on the system. So honestly, I was worried at Google, working at Google, and I was always arguing about, so what is the right isolation for containers? And I was more in the camp of, well, containers should be doing very well, right? If you harden Linux and if you have these runs, it should be good enough. But this Dirty Cow came up, and it was a different security team, but they mentioned that, yeah, there's Dirty Cow, and this one happened. Then that really opened up my eyes that, okay, so if it's a complex system, then literally we have to be prepared for unexpected situation. So to be fair, there are tools for experts. I'll see why I say experts, but one is SE Linux and AppArmor and more based on a Linux security module, which is a mandatory access control, which provides fine-grained access control per process. So it will really, you can describe very well on what a process can do and cannot do. The second one, SecCom BPF. SecCom is a kind of short for secure computing mode inside Linux. And this -BPF, the bucket packet filter, it's a filter by itself. But what it means by the SecCom BPF is that you can actually specify the policy by using a language coming with the BPF and apply it to SecCom. And it's an extension of that, and you can define, which syscall should be filtered with that BPF rules. Just to kind of give you an example, before coming to Kubernetes Engine team, I worked at a Chrome OS team, and I actually did bring in Android apps to Chrome OS. So I had a kind of a luck to look into both Chrome OS and Android at the same time. And it's interesting to me because Android use SE Linux intensively, and the Chrome OS use SecComp intensively. What it means that is SE Linux in Android, working app compatibility is very important. So you actually want to have Y syscall to cover or the framework to cover. Therefore, you need to harden the Linux kernel very strictly. And they even have a test suite and also the policy that you have to get certified to be named as Android. On the other hand, Chrome OS, they're using SecCom BPF to sandbox the Chrome browser rendering. And the philosophy there is that to reduce the attack surface, because there's only browser. There's no, the browser is an application framework, so all you wanted to focus is what the browser is going to send to the system. So yeah, we have a system, and the question is, are these tools for me? Maybe for you. And if you do know, the policy very well, if you know what application you want to put, like I said in the Chrome, Chrome, in the case of Chrome is just a browser. If you know, and then it's great. But the problem is that the more descriptive the more detail you describe in a policy, the chances of that policy to be generic in other process will be lower because it's very specific. So first of all, your app may not run with those policies. So the isolation-wise, we have another one, called making a VM as isolation boundary, which is true. But then the downside there is that, well, you have to launch a VM, and then you have to run a kernel, large or small. It's still a kernel. It's for just one container or one process. It's not necessarily effective or elastic as a regular process. So okay, so we talk about various things. There's no pros and cons. So what do you think, Ian? Do you think? Or do we have all the right tools for us? What do you want?
Right. So at Google, we looked at a number of different solutions, right? We talked about, we looked at things like seccomp, we looked at things like SE Linux and AppArmor, and we looked at things like VM solutions. And there's trade-offs between all of these different things. And so the thing that we saw, that we would have to make trade-offs with is that we wanted our containers to be secure so that attackers that have gotten control of the container can't break out of the container. We wanted something that was less configuration, or ideally zero configuration, something that was kind of like a self-driving car here, where it's kind of turnkey solution, something we can just get in and go. We don't have to configure per application filters, or per application write some sort of SE Linux or AppArmor policy. We want to just be able to run our applications unmodified. Another was that we wanted to have something that was lightweight. We ran a lot of containers, and so we wanted something that gave a similar experience to what we were used to. So we want something that's lightweight, doesn't use a lot of resources, and gives us low memory and CPU overhead. And so we looked at these, and we saw that we had to make a lot of trade-offs, but we thought, what if we didn't have to make these trade-offs? What if we could get everything that we wanted in a system? We could maybe make different trade-offs and then get all of the things that we wanted here. And so we came up with something called gVisor. So gVisor is a sandbox for containers, and it implements an independent user space kernel. And so this runs in user space, separate from the Linux kernel. So it gives you an extra level of isolation. And so as we were doing this, we were the Linux system call interface is this, wide attack surface. But you can think of it kind of like an API. The Linux kernel provides you an API that your applications then use to execute themselves. And get resources. So what if we just made a different implementation of that API? And we ran that in user space. And that's how we came up with the idea for gVisor. And so it's a user space kernel that implements these system calls. So it's similar to something like user space Linux, except for we have our own kernel rather than trying to run Linux itself in user space. And so this gives us the kind of high security that we want. It's a user space kernel that implements these syscalls, and it's written in Go. And the reason why we did it in Go is because we got a good trade-offs when using Go between the memory and type safety of the language runtime, as well as the speed. And we also get this kind of Linux user space kernel so that even if the attacker gets control of the container application, then they find some sort of bug in the gVisor. Even if they do that, they still don't have control of the system. They're still stuck in user space. So they can't just execute everything as the kernel and get full access to the whole host. gVisor is also zero config. We can run unmodified Linux applications because we implement the Linux syscalls. Applications we can just run them in the sandbox and have them use that kernel. And so we don't need to write any filters or profiles, or like security profiles, things like that, in order to get the least privilege for our applications. Typically, for those type of filters, you would need to know what the application needs to use, what capabilities it needs, what syscalls it's using, and what sort of resources it needs from the operating system in order to actually configure your least privilege for the application. But with gVisor, we can just run the application in the sandbox, and we don't need to do these kind of configurations. It's also very light and quick, so it's very similar to the kind of experience that we got when running normal containers, right? So we have basically a 15 megabyte or so memory footprint. This can kind of change depending on the application and how it actually uses the gVisor user space kernel. But in general, you get something around a 15 megabyte memory footprint. So you get just that amount of overhead. And also, you can start up applications in around 150 milliseconds. So this is very similar to the way that the containers run. We don't have to start up have a lot of startup time or a lot of overhead associated with our sandbox. So this really fit well with our kind of model and fit well with our kind of container orchestration within Google. And so we use the gVisor for a number of things within Google, but one of the more obvious things that, like Yoshi mentioned, and this is a tweet from our director, Oren, we use it within Cloud Platform particularly for things where users need to upload application code, and we run it on their behalf. So we don't want to have a situation where somebody can upload code and then get access to somebody else's application or break out of a container and then read some other user's data. That would be a pretty bad security breach. So what we want is to provide a sandbox to run these applications. And so for things like App Engine, Cloud Functions, and Cloud ML, this is a perfect fit for us in order to run applications within a sandbox like this. And then we decided that this was a particularly interesting technology, and this is something that now that containers are becoming more ubiquitous and more popular, and things like orchestration systems like Kubernetes are starting to become popular, and people are starting to build PaaSes and all kinds of different systems on top, we thought that gVisor would be something that users outside of Google could take advantage of in order to provide these type of solutions. And so we open sourced it, and it's now it's on GitHub at github/google/gvisor. We open sourced it in May this year at KubeCon, and the response was enormous. Like, it was quite a lot more than we expected. Within 10 days, we had 5,000 GitHub stars, and we have over 6,400 today. So thanks to all of you who have started GitHub and us on GitHub and who are kind of following the project. But the response has been enormous, and we're really kind of interested in how we can kind of take this further and integrate this with other kind of Kubernetes and other orchestration systems. But before we do that, let's take a look back at the actual architecture and kind of dive a little bit deeper into the architecture of gVisor. So gVisor is a system for running a sandbox, and so we have our user space kernel, but we wanted to make something that made it easy for folks to run containers in our sandbox. And so we provide a OCI interface, OCI compatible interface. So if you're a Docker user, you may be familiar with runc, which is the OCI runtime for containers. And gVisor provides a command called runsc that is essentially a drop-in replacement for runc. And provides this OCI implementation. So we can run OCI bundles for containers in a sandbox very easily. And so once you start up a container, that container's application is loaded into memory along with the Sentry, which is our kernel in user space, and the application is loaded into the Sentry's user memory, and then the application is executed. But as we are executing it, the Sentry has two different types of modes. One is a KVM mode, and one is a ptrace mode. And what these do is these intercept the syscalls that the application makes, and then handles them inside the Sentry, so inside of the user space kernel. So we don't actually go into the kernel in order to handle a lot of the syscalls that we're making. The Sentry does actually have to make a few syscalls to the Linux kernel itself, but that surface area is highly reduced compared to a normal container. So Yoshi mentioned that we had 319 total syscalls for the Linux syscall API, and the Sentry narrows that down to a surface area of something along the lines of between 10 and 20. So something like that. And then we have, and because we know what the Sentry needs in terms of its own syscalls, we can then put a seccomp profile on that and further lock down so that only those syscalls are the ones that can actually be run by the Sentry. And so even if an application, somebody's able to take control of an application, and then they find some sort of bug in the Sentry, some sort of buffer overrun or something like that, that they're able to execute code as the Sentry, they're still locked into this user space sandbox that can only run a few syscalls. And so you're not actually able to do anything very much at that point. The sandbox actually can't even write to the file system. When applications need to write to the file system, the Sentry writes to or uses a separate process that we start up for the container called a gopher. And we use the 9p protocol in order to to do file I/O and things like network I/O. So that type of I/O is not something that you can actually do just unlimited, even if you can take care of this, even if you can execute code as the Sentry. So this gives us quite a good sandbox for applications to run for untrusted code. It gives us a very good set isolation from the kernel. But as we said, like everything that you do is trade-offs, right? I said that earlier that we didn't want to make the trade-offs between security, zeroconfig, and having lightweight containers, but that means that we have to make trade-offs in some other place, right? And so there are some things that we have to add as caveats to running things in gVisor. So some applications. Let's walk through some of the applications that might be impacted by running in a gVisor sandbox. The first of those is syscall-heavy workloads. So because gVisor is implementing these syscalls in user space, it's a kernel that's using the Go runtime. And just by the fact of it's being run in user space, there's a slight difference in things like running kernel code is run as a higher priority on the CPU and things like that, so you will get some performance impact. So applications that might run lots of syscalls in a tight loop, those are the type of applications that are going to be impacted by running, performance-wise, by running in gVisor. There's also the idea of syscall coverage and compatibility. So gVisor itself implements many of the Linux syscalls, but it doesn't implement every single last one of them, at least not currently. And so there's a total of 319, but we implement around 211, and those are some of the more highly used ones. But it also means that applications that use those syscalls that we don't implement will have some compatibility issues. The last thing that I want to highlight as a caveat is direct access to hardware. So applications that need direct access to hardware are potentially not a great fit for gVisor, and that's partly because just of the nature of the fact that we are running in a sandbox. Providing direct access to hardware from a security standpoint is very risky because you have direct access to the hardware. You can do whatever you want. So if the application is compromised, the entire host is generally compromised. And so gVisor doesn't have the concept that a normal Linux kernel does of device drivers and things like that. And so direct access to hardware like GPUs or other specialty hardware may not be a good fit for gVisor, at least not right now. Great. So that's out of the way. Let's actually take a look at a couple of the vulnerabilities. The first one is Dirty Cow, and the second one is Meltdown. And we'll just kind of take a look at how gVisor might mitigate a couple of these vulnerabilities, and kind of explain what they do, and then how gVisor kind of mitigates them. Thank you. All right. So let's switch over to the demo machine.
Can we switch?
Yeah, can we switch over to the demo machine here?
Thank you.
All right, great. Let's make this a little bit bigger. So what I'm going to do here is I'm going to use I'm going to run an application that makes use of the Dirty Cow exploit, and run this in just a normal container to show you what happens when you do that. So what happens here is, what I have here is I have an OCI bundle. So this is just a regular container. So you can think of this as just a container that's been unpacked, or a container image that's been unpacked to the file system, and we're going to run this using runc. So if we just do like n20 here of the config, we can see we're going to run an application here inside the container. We're going to write some data to the exec password. We're running this as a user, not as root. So normally the user wouldn't be able to write to this file. What we're going to do is we're going to write this little string here, spam, into the exec password file, which is not something that you would normally be able to do, but because of Dirty Cow, exploiting Dirty Cow, you're able to do that. So when we run it inside a normal container, we're going to do sudo c run. We got to give it a name here, so we'll just say Dirty Cow. So when we run this application, what this is doing is it's taking advantage of a race condition in the Linux kernel. What this is doing a couple of syscalls in two different threads at the same time in a kind of a tight loop. And when it gets at the kernel state in just the right place, it's able to write to a file that regardless of what permissions are associated with that file. And so what we're doing here, this uses two different syscalls. One of them is the madvise syscall, and one is a ptrace syscall. But the madvise syscall is one syscall that is highly used in normal applications. So this is something that's very hard to actually filter out of an application. So you can't necessarily just put on a setcomp policy that you can't run madvise or something like that, because madvise is used in pretty much every application out there. So even if you're able to know what your application uses for things like syscalls, you're not always able to just filter out those syscalls. Like some of them you actually need to be using. Okay, so here the application's finished. It's run through our tight loop and has been able to take advantage of Dirty Cow. And so what we'll do here is we'll take a look at the, actually we need to look at the root file system here. And we'll look at the password file and scroll up here. So we're actually able to see here that we've written to the beginning of this file here. So you can imagine that we could overwrite just lines in this file, add a new root password, and just get privilege escalation that way. So it's very easy to get privilege escalation when you can just write to any file on the file system. So this is something that's really, really bad for us. So let's switch over and take a look at running it in gVisor. So when we do this, we have the exact same OCI runtime here, or the same OCI bundle. We're going to do a show you here just the exact same configuration. We're running as the same user. We're using the same application. We're going to write to the same file and the same with the same content. But this time we're going to use run sc for gVisor. So we're going to do sudo run sc. I'm going to add a couple of flags in here just to show some debug information to show you what's going on, because otherwise it would just kind of sit here and run. All right, so when we run it in gVisor, we're able to actually run the application, and the application executes exactly the same way as it would inside of a normal container, except for what it's doing here is it's running in 2 different loops, or in 2 different threads, and executing madvise and ptrace over and over again. And so what this is doing is just spitting out logs every time the madvise and ptrace are called. But you can see here the application's actually running, but in the end, we won't actually be able to write to the file. So if we go in here, actually, I should open up another SSH, and then we'll just look at the file and then kind of verify that the file has not actually been written to. Let's do this, right, and then we say root file system, exec password. So we look up here, we can see that we haven't actually been able to write this. And by nature of this particular attack, the attack will just continue to run and try to take advantage of the kernel. And as long as it's not able to, it's just not able to write to the file. But it's also kind of interesting to note that this is exactly the type of application that can have a performance impact in gVisor, because it's running in a tight loop and just executing syscalls. This is actually a worst case scenario for that. But normal applications aren't doing this type of thing. All right. So we're able to see that we can mitigate vulnerabilities with like dirty cow, and that's a kind of a pure Linux kernel vulnerability. But what about for other kinds of vulnerabilities? So Meltdown is another vulnerability that's very popular, and Meltdown is a combination kind of hardware vulnerability as well as a software vulnerability. So this is something that, because gVisor is a software sandbox, we can't 100% mitigate hardware vulnerabilities. But in some sense, on the software side, we can mitigate it a little bit. So for instance, we are going to run an application and use Meltdown. And what Meltdown does is it's kind of it takes advantage of a hardware bug in like kind of conditional execution. And so what you have is, but the most easy way to take advantage of that is in a situation where, in the past, when applications were run, they would map kernel memory into the process itself. And so, if you do that and you have this hardware bug, you're very easily able to have the application read that, be able to read that kernel memory in any place, not just places that you're able to read, but ones that you shouldn't be able to read. So here, what we're going to do is we're going to get the memory address of the Linux proc banner. So this is something that's part of kernel memory. So when an application is run, this kernel memory is mapped in, and then what we're going to do is we're going to tell our application to read this particular piece of kernel memory, this address from kernel memory, that it normally shouldn't be able to read. So we just look at this. It's actually, oops. All right. So like this is just an address in memory that we want to try to read. So if we run this in a normal Docker container, oops. All right. So we're going to run this in a normal Docker container with runc, and we're going to give it the address that we have here, and have it read out that memory. So when we do that, we're able to see that the application is vulnerable, and that we're able to read out the memory. And the Linux proc banner just has some information about the kernel version and some other information. So that's not particularly bad, but other types of reading other parts of kernel memory could potentially give you lots and allow you to do lots of different types of privilege escalation. So when we run this using the same way, but we run it in gVisor, gVisor actually doesn't map in this kernel memory, and so we're able to mitigate this slightly. I didn't run this with sudo. Oh, no. Ah, yes, you are right. So we run this with gVisor. We're able to see that it's not vulnerable, and because the kernel memory is not mapped into the process, that we're not able to actually read that memory out from Linux proc banner. So in that sense, some things can be partially mitigated. There are other kind of theoretical ways that you could take advantage of Meltdown in gVisor, but those are things that we think are a little bit harder to actually get working because gVisor has a hardened sandbox. All right, great.
Thank you, Ian. Then back to the slides, please. It's our probably first time doing the demonstration on stage, so it was great to actually see this in action. Thank you. Appreciate it. All right. So gVisor and Kubernetes, both were invented at Google, and we democratized that with open source, both Kubernetes and gVisor. And by the way, gVisor, if you like it, there are a couple things you could do for us. You could go to GitHub, press start button. You could fork it. We have around 300 forks, so if you have interest in projects, absolutely please fork it. We'd love to hear what you could do. And also, perhaps most importantly, like Ian mentioned, gVisor took a different kind of a trade-off, which was syscall compatibility. If you can try running your application or didn't run, file a bug, let us know, and let us know your use case. I think that's what we would love to know, just only with gVisor. But we want to make this gVisor accessible to everybody through Kubernetes. We're leading the effort of introducing the concept called Sandbox pods specification in the Kubernetes community right now. And of course, gVisor is one of the runtimes that have been proposed for Sandbox pods in Kubernetes. What it means is that, well, Ian is a great hacker, so he can type in a command nicely. But it's not. We want to make it more generic, meaning if we could actually let people access to gVisor, use gVisor through Kubernetes API, how wonderful that could be. And I'm going to quickly talk about what we're doing in the community as we speak. So sandboxing Kubernetes, it's not done yet, unfortunately. It will be great to finish up and talk wild, and yeah, we're done, but just see work in progress, really. Work in progress, but it doesn't mean that we're baking things inside Google. We're really doing everything in open source. So if you look at all the open source discussion, you'll see our Tim Alclair, our tech lead for this project, and he's making huge progress. So the Sandbox pod, so Kubernetes API, new Kubernetes API for the Sandbox containers or pods. It will be a pod level isolation. So pod, for people who don't know what the difference between pod and container, well, it's kind of similar, but pod is the kind of the smallest granularity, the primitive that could be scheduled by Kubernetes. And inside that pod, you could have multiple containers. So it will protect this group of containers as pod. We hope that for anything that's going to be part of the sandbox pod, we'll have at least two, like multiple layers of isolation boundaries, because otherwise it doesn't make so much sense to call it a sandbox pod. If you could break up, what's the difference? This is the really work in progress API. I have more detail, but I just decided to not to put too much. This is actually the third version. When I started working on Slide, this is the third version I had changed. So as we speak, we're making change. But I think Tim already has the very close to final form as a submission. So we'll see how that lands in the future version of Kubernetes. So just to kind of give you a sneak peek, Runtime Class is a new API to specify the runtime, meaning like which runtime that I want to use for my pod and containers. You can specify which runtime class to use from the pod spec. So Tim, kind of emphasized that, make it V1 alpha very clear. Yes, it's still working on. So the name will be runtime class, and in this case, metadata name will be gVisor, and the runtime handler will specify, another gVisor, which is another thing. And inside there, it was by which file of the runtime to use and all the relevant specification. But that's something that we believe that the cluster operator, so if you're running on-premise, the cluster admin will be in charge for setting that up. And in case of cloud, it will probably be us. Like cloud operator providers will be configuring the left side of the configuration. And all you have to do, users have to do, is to write up a regular pod spec, in the spec that you specify runtime class name, and choose whatever you want to. We talk about gVisor today, but there are also other approaches like Kata container. So we're working together to standardize this specification. I think we're making huge progress there. So we talk about the container isolation, from the past and the present. The past is like iteration, and the present is what we have open source, what we have in Kubernetes and gVisor. And of course, we just talk about a little bit of future to bring it together. So if you're interested in gVisor, running gVisor with Kubernetes Engine, please let us know. We will love to hear your thoughts there. So this is a link to our forum. We'll continue the discussion and the conversation. Thank you. We ran out of time, so hopefully we could take questions after that. Thank you.